Hello everyone, we're going to restart the presentation, so if you can make your way through the auditorium, thank you.
It's working, I think. Yeah, it's good to know that the pressure's off. We've had talks for about 2 hours, and it's been great. Okay. It's been really exciting. Sometimes it just happens. So just read the room, I guess. Okay, so let's make a start. Yeah. Great, we're going to make a start with David Silver now from DeepMind and UCL. So we're running well over schedule now, so please quieten down and we're going to make a start. Thanks, David.
Hi there, everyone. Can you all hear me at the back? OK. So thanks for the invitation. It's really nice to be here. It's really great to see the London community so strong and vibrant and see everyone here and great talks. Long may that continue. So I'm going to talk about deep reinforcement learning and kind of tracing through a particular line of research through the last several years. Of course, there's a lot of work that's gone on in this field which connects to deep reinforcement learning, which I won't have a chance to touch on. So in some sense, it's like a personal journey. But I hope there'll be something to learn about along the way, and maybe something new even for those of you who've seen some of this before. OK. So I wanted to start with this one slide to really, I hope it's provocative for you. I think of it for really, this is my personal motivation for why I think that deep reinforcement learning is actually important. And it's kind of condensed onto this one slide here, which is to say, what's my goal here? Well, it's actually a really ambitious goal, an ambitious goal which maybe if we were able to achieve it would have really big long-term consequences, which is to try and build an artificial agent with human-level intelligence. So some people refer to this as AI or AGI. It's a big goal, and we're a long, long way off. Okay? But how should we get there? Like, what's the path to try and get there? And I don't want to kind of claim to have the hubris of saying, this is the way, or even that there aren't other ways. I just want to suggest some conjectures that might lead you to trying this particular path as one way that might actually carry us a long way towards this goal. Okay? So the first conjecture is about the problem. Like, forget about how we actually solve it. Let's make sure that we're solving a well-formalized problem that we think actually will carry us all the way towards this goal of human-level intelligence. And so for this, I think one reasonable approach is to think of the reinforcement learning problem. This problem is kind of illustrated in this figure you've probably seen before in the upper right here, where we have an agent that interacts, receives observations from its environment, gets to take actions, and gets some kind of reward signal in this ongoing loop, and it's trying to maximize that reward signal. And so the conjecture is that problem is actually enough to formalize the problem of intelligence, that it's enough to capture all of what's meant by goals and goal-seeking behavior and all these notions of intelligence that people think about can be captured by appropriate formulations of this particular loop, instantiating the right rewards, the right environment, leading to the right observations. And so that's the conjecture, okay? You don't have to believe it. I'm just putting it out there as a conjecture. The second one is maybe more familiar to people in the machine learning community, which is about the method by which we choose to solve the problem. And for that, the proposal is to use deep learning as the mechanism to actually try and, if RL gives the objective, the problem we're trying to solve, and we've got a well-defined kind of optimization problem to maximize this cumulative reward signal, then what mechanism should we use to try and get there? And for that, deep learning might be one choice. And the conjecture there is really that we should choose deep learning because deep neural networks can represent and learn any computable function. That's the conjecture. The first part of that is kind of well established. That's the universal function approximation theorem for neural networks, that you can represent anything with a big enough neural net. The second part of that is the subject of a lot of study at the moment, that you can essentially learn anything with a neural net. But there's increasing evidence that at least for very useful classes of function, that seems to be true. And so the hypothesis of deep RL, the conjecture that combines these two things together, is that we should combine the problem definition of RL with the solution approach of deep learning. That RL will give us the objective, and we use deep learning as a kind of a workhorse to try and give us the method to actually optimize that. And in doing so, we can actually solve the big problems of intelligence. And of course, this obscures huge amounts of detail of how to do this well, and that's the subject of numerous lifetimes worth of research. What I want to say is that this is one approach we can take. This talk is about some steps in this direction of trying to pursue this hypothesis, these conjectures, and showing that at least for some problems that were considered hard in the past, we can make considerable progress. That's not to say that we've gone all the way, and of course there are many, many hard problems of intelligence for which we're nowhere near. But maybe this is a beginning. Okay. So how can we evaluate progress? If that's the goal, if that's the aim and the ambition, how can we know how well we're doing? Well, there are many ways to evaluate progress. The path that I've enjoyed pursuing, if you like, is to use games. Games as a way to evaluate how well our agents are doing, partly because it's very easy to compare them to human-level intelligence by simply competing against humans and seeing how well we do. If you can beat a human at a game like chess or Go, you know something about the level of intelligence that you've achieved. And so this talk is really about concrete instantiations of this for board games, video games, and trying to see how far that idea can be pushed. Of course, games miss many aspects of the real world, but at the same time, they are enormously flexible, and there's a lot that can be put into a simulated game environment. And I think there's a lot of interest there and challenge there, and a lot that we can learn. OK. So to begin with, I'm going to take you back a few years. I'm going to try and rattle through these first ones reasonably quickly and try and get to things which maybe are newer for more of the audience. So apologies if there's things you know too well or too unwell. It's always hard to get these things right. OK, but this is about how to try and get something like human-level intelligence within this limited domain of Atari games. So this is work back in 2013 to 2015. And so this really is the first instantiation of this RL problem that we'll see, where really now we've got this brain, and it's being plugged directly into this Atari problem. Literally, you've got something where someone is providing as your environment this Atari emulator. There's some cartridge which gets stuck into this thing. You don't know what that cartridge is. You don't know how the Atari emulator works. And you basically just see the pixels of this thing and the score, and you get to control the joystick and see how well you do. And the aim is to try and do better and better and better. And so the approach which we took and introduced those many years back was to actually put together a deep neural network in the form of a convolutional neural network, which processes those pixels, converts them into an estimate of how well you're doing. What score do you predict you will get from that particular screen that you see in front of you? How well do you think you'll do in the future? And if you can do that for all of the different actions that you could take on your joystick, then you can also use that to play the game. You just pick the action with the highest predicted score. And that solves the problem. Okay? So this was known as DQN. And here's some some videos of the initial kind of approach that we took to do this. So these are examples, really, where the computer's never seen the game before, and it didn't know the rules. So it learned by this approach of DeepRL just to maximize its score, just given the pixels and the game score as input. But we did this separately for 57 different games. So it was like the agent was born in one of these particular environments, and it had to learn in one of these games, like this tank game on the right or Breakout on the left. And then over time, it just was exposed to experience and had to do better and better and better until eventually it learned how to do very well in these problems. In fact, on this one on the left, you see that it kind of learns this strategy over time, where it eventually kind of figures out that, not just to knock the ball back, but eventually it figures out a new strategy that the human designers didn't know, to actually tunnel through on the left-hand side of this breakout and bounce the ball at the top. And that actually gets a lot more score than you might have predicted if you didn't know how to play this game. OK, so this is something we can do. We measured the performance relative to humans, and we found that we were roughly, across all of these different 57 games, able to achieve something like human-level performance, about 75% median performance relative to human scores on these games, by getting a kind of a decent gamer to play all of these different games. So in some sense, that's setting down a marker and saying, OK, we have something. We have something which can complete this loop of deep reinforcement learning. It can learn directly from this stream of experience. There is a sense of feasibility, that there's some traction in this direction that it's possible to learn, at least within this suite of kind of simulated video games, to do well and learn some of the skills that humans have. But what happens if we really try and push this to harder domains? And so the remainder of this talk is kind of trying to go beyond this and see where we end up. So I want to talk next about the game of Go. So this is about the program AlphaGo, which became the first program to defeat a professional Go player a few years ago. And why is Go interesting? Well, Go was for many years considered to be exactly one of those challenge domains where if you were able to succeed in Go, it represented a step forward for AI. It was considered very hard. It was considered to be something where the existing AI methods were insufficient to be able to make progress. And people felt that something new was required, something radically different. Lots of people thought that you couldn't evaluate a Go position in a way that could predict what would happen, or that you would need kind of special human knowledge to go in there. And so there was a sort of mystique around it. And also it's kind of canonical. It's an old game. It's played by a lot of players in the world, and it's very large and complex. And so this is just an illustration of what the game actually looks like in terms of if you try to take the methods which were around in those days, like these tree search methods, and try to expand the tree, there's this huge explosion in the kind of state space that you have to deal with, where there's around 361 different moves, and from each of those, 361 further moves that can be selected, leading to this huge blow-up in the sort of state space that you have to deal with. And that was intractable to many of these kind of search-based methods that were there at the time. So what we chose to do was to apply the kind of methods to do with deep reinforcement learning that I mentioned at the beginning of the talk. So from the deep learning perspective, what is this function that we were trying to represent? I said that we're trying to harness the power of neural networks to represent the appropriate function. So what is the appropriate function to be able to play the game of Go well? Well, in fact, we chose to learn two functions. We chose to learn both a policy and a value function. The policy, which we call the policy network here, is essentially something which is trying to predict what the best move to play in any position is. So the policy network is fed in the position, just as like raw inputs describing where there's kind of black stones, white stones, empty points on the board. It processes this through a deep convolutional neural network to kind of give more and more sophisticated features describing what's going on in that board position. And at the end, it outputs like a probability map, a policy saying for each of those kind of board positions, what's the probability of actually playing a stone there. And so it's like a move recommender. You now have something that can say, in this position, I think you should play here. And so that's a kind of fundamental function which is useful. If we have this, you can just play the game of Go. The second function which is very useful is what we call the value network. And this is trying to do something different. It starts again with the position, evaluates that with a convolutional neural network, builds up a representation that's used to actually then evaluate who will win from that position. Like, is black going to win or is white going to win from this position? am I going to win or is the opponent going to win? So it's kind of just trying to predict this signal of +1 for a win or -1 for a loss, and try and get this neural network to learn from each of these positions what the outcome would be. So the way this was done in the original AlphaGo, and I'm going to kind of go quickly over this so we can go to a later instantiation that I think was a little bit more elegant and powerful, was that it was initially trained from human expert data. So it was shown a whole load of human expert positions from professional play and very strong players. And for each of those positions, we use supervised learning to essentially classify the move that the pro player played and teach the policy network to pick the same move as the pro player. Okay, so it's just classification, supervised learning. Do the same thing as the human does in each of these positions in your data set. So that's the supervised learning part of the training. That gives rise to a policy network. That policy network's pretty good, but it turns out that mimicking humans isn't really enough to actually play as well as humans. You really want to have something where it understands for itself what's good and what's bad. And for that, we use reinforcement learning. So we basically got the policy network to play games against itself. And then you look at the outcomes of those games. And you say, OK, well, when the policy network played games against itself, either black won or white won. And from each of those positions, you now train, by regression, a value network to predict the winner of that game. So for each of those positions that you see, you want to know from that position who ended up winning. Did I win or did my opponent win? And that's what the value network is trained to do. Okay? And that gives you your two functions, these two kind of fundamental things. So it's combining the problem definition of RL here with this kind of representation power that you get from the deep neural networks to be able to essentially learn the function from scratch, from these raw inputs, that really learns the shape of whatever that function needs to be. So the way that we used that in practice was to kind of replace the brute force kind of search, which is infeasible in the game of Go. So if you think of exhaustive search, I mean, this is just like a cartoon of the exhaustive search. This is only showing like a binary search tree for a fraction of the, really you're branching 361 ways at every single node, and really this whole search tree is of depth about 200. So it's an enormous search tree in practice, but just to illustrate that, the main idea is that we use the policy network to kind of reduce the breadth of this search tree. So instead of considering all 361 possible actions you can take, you kind of use the policy network to suggest the best moves amongst those. So whichever one's a high probability, you sample those, and that sampling process means that your search focuses on the most plausible moves initially, but eventually you try everything, and eventually you will overwhelm that prior and explore other things too. And then we reduce the depth of this search tree by using the value network. So this is just like the evaluation function of your classic chess program, if you've ever played with one of those things, where you come down to this depth here, and each of these V's here kind of represents your estimate of what would happen if you were able to do a complete exhaustive search from that point onwards to the end of the game. So that would be infeasible. So instead, we kind of use the value function to kind of cache that knowledge. It's like a cache of what would happen if I was to do an optimal search from this point onwards. And that cache becomes very useful and becomes the thing that helps us to reduce depth and mean that now you only need to search a fraction of the breadth and a fraction of the depth, and suddenly you've got something which is tractable. In practice, we use something called Monte Carlo tree search that combines those ideas in a more kind of flexible anytime way, but the principle is still the same. So we put these things together, and we actually played a game, so this was back in 2016, against someone called Lisa Dole, who was a 9-dan professional player, the winner of 18 world titles. So he was, at the time, the greatest Go player for over that previous decade. He'd kind of won everything multiple times. And at this point, we were, I think it was unexpected that there could be something which was able to actually beat human players. We just showed for the first time around this point that we could beat the first professional player of any kind, and now we went and played the world champion, and AlphaGo actually won the match 4-1. I thought it would be fun just to share what it was like a little bit to be there. It was quite an experience. I have to say, when you come from academia, you sort of expect that you do a piece of work and then maybe 12 people will read your paper, and if you're lucky, 4 of those will cite it. And I realized only when arriving in Seoul for the event that this wasn't like that. That actually, there were the room was rather busy. Let's say. I hope this is going to play.
The simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lisa Doll.
A match like no other is about to get underway in South Korea.
They said all is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lisa Doll find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Well, look at his face. That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong. Yeah, it's made a mistake. It's got to be a miracle.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
Thank you. Oops. No, not that one. You gave me a round of applause. I thought maybe I could get another one if I play it again. Just to Okay. So one of the interesting things which happened during the course of that match was we started to discover a little bit about how far this paradigm can be pushed. One of the questions people have often when you start to build something which is pushing at the limits of human capabilities in the domain is they start to wonder whether there are areas of human capability which are maybe privileged or special, which a computer couldn't have access to. And in Go, one of those things was creativity, that people, particularly the Go masters, felt that there was something special about this game and that the human creativity was something which would always lead to some kind of special advantage. And I think one of the interesting points that happened in this match was a move 37 of the second game, where it turned out that AlphaGo played something which actually the Go professionals found to be extremely creative. And so it kind of changed the way people thought about AlphaGo in a certain sense, that actually perhaps it wasn't just humans who were able to be creative, but AlphaGo itself. And this is the reaction of the commentators. This is a 9-down professional looking at this move being played, and they're staring at it, and they're saying, this can't be right. I thought it was a mistake, they say. I thought this was a mistake. And that was everyone's reaction when they saw this. It was like so surprising to human pro players that they just couldn't see how this thing could actually be anything but a mistake. So I think, if there's a lesson there, it's that we should maybe trust in our principles, go back to what we believe as machine learning scientists to be the right principles, and a lot of the things which maybe people speculate are beyond the capabilities of those methods may turn out to be within scope of what can be achieved. And at least within this one domain of Go, that was an example where that turned out to be the case. I don't want to kind of claim too much or too strongly that that's been demonstrated anywhere else, but at least there are examples where that has been true. Okay. I wanted to move on and just so AlphaGo was a few years ago, and I really wanted to spend most of this talk today talking about what's come since and share with you some of the later work which maybe people are less familiar with. And where I wanted to go next was actually a step that we took to try and take that method and generalize it in a way that it could be applied to not just Go, but many domains. Like that feels like much more like that original goal that we were after, something where we could just drop something in and it will just work and achieve something like human level intelligence in the domain that you place it into. That's the thing we're after. So taking a step towards that, we try to expand beyond just Go to at least within the domain of board games. Can we, within these board games, expand the scope of what the algorithm can do to be able to just drop something in, whether it's Go, chess, or some other board game, and actually find something which can learn for itself how to play at the highest levels of human intelligence. So this work was called AlphaZero. And so really the key principles were these, that we started and we wanted to learn really from as much from first principles as is feasible in this kind of approach. So we wanted to start with no human data. So unlike the original AlphaGo, this system learns solely by self-play reinforcement learning. So it just plays games against itself, starting from completely random behavior, and everything else has to emerge from the system, no human data to start it off. It has no human features, so it only takes the raw board as an input. Okay? So there's no human saying, this is a good feature or a good thing to look at or something useful in this position. And there's no domain knowledge. So in particular, it's only given the rules of the game, no special treatment for the game of Go. Okay? And so how far can we get if we take those things away? You might think we'd be losing out. But it turns out that actually sometimes the more knowledge we put in, the more we end up handicapping our own systems. And that by stripping those things out, sometimes we actually take away our human biases and allow the system to do better for itself than actually us imposing those biases upon the system. And this turned out to be one of those cases. So the actual approach we took, I'm just going to talk through the algorithm in a little bit of more detail now. Okay, so the approach that AlphaZero used is to start by playing games against itself. And these games were played using search. So the idea is that from each position that this kind of game starts from, so imagine you're in some kind of position here, like this empty Go board here, and you run some search here now, using your current policy and value network to kind of guide the search, to reduce the depth and breadth of the search. And as a result of that, you end up picking a move. Then play that move. Play the move that's recommended by the search. And that gives you a new position. You run a new search, play a new move, and so on. And AlphaZero plays games against itself in this fashion. And the point is that by playing games against itself, we end up with outcomes at the end of this, a winner, which is a very high quality outcome. Like this is the highest quality teacher that we actually have access to. It's AlphaGo, in some sense, playing games against itself, using its full search engine. That really gives you a very high quality estimate of what's really, a high quality sample of what's really likely to happen if you were to play at a high level in this game. And so given these high quality games, this kind of teacher, the best teacher we can have being ourselves, we then use that data to actually train new networks. So we use the data in particular to train, first of all, a new policy network is trained to predict AlphaZero's moves. So here now we see that for each of those positions we went through, we end up, for each of those positions, saying, well, what move, let's get our policy network, that's this thing here, to actually predict the move that the whole of AlphaZero actually played. In other words, we're trying to get the raw network to immediately give us the thing which the whole of our search gave us in the past. So if you were to run the whole search, invoking your neural network multiple times, doing a Monte Carlo tree search, doing this big look ahead, looking ahead multiple steps, and then at the end of that, saying this is the best move to play, we want our new generation of policy network to predict that best move straight away without having to do any search. And so that process is how we end up kind of training a new policy network. From each position in our data, we train our own search-based recommendations of what to do. And at the same time, we train a new value network that's trained to predict the winner of that game of self-play. So from this very high-quality search-based game, we look at who won that game, and from each of those positions, we try to predict, well, did black end up winning that game, or did white end up winning that game? So we're basically looking at what happens when we play games with the best quality games we can get our access to, who ended up winning, and train a value network to predict those outcomes by regression. So we kind of learn to predict those things. Okay. And all we do then is to iterate that procedure. So now we have a new generation of policy and value network. So that policy and value network, which is now a much stronger policy and value network, now gives us much better guidance of how to actually search. And as a result, we end up playing much better moves in our search and picking better moves that leads to better quality outcomes and better quality kind of targets for the next generation of learning and so forth. So better networks lead to better data, lead to better networks, lead to better data. So that's the cycle that's used in AlphaZero. Okay? So how well does that work? Well, we first of all applied it to Go, and we ran it. This red line here, this is an ELO scale. This is roughly the same kind of scale you hear chess players talking about. So an ELO scale roughly means that if you're 200 ELO points higher than another player, it means you win 75% of the time against them. That's the kind of semantics of ELO. And so here we have the AlphaGo version of AlphaGo that played against Lee Sedol, the one that we saw that video for just now. And what we saw is that after just 8 hours of this self-play training, starting completely from scratch and just using this reinforcement learning combined with deep learning approach, AlphaZero was able to exceed the performance of that version of AlphaGo. And eventually, it reached this level of performance that was able to defeat all previous versions of AlphaGo, which was by far the strongest Go program around, by 100 games to 0. OK, so it works well in Go. What about other domains? Oh, before we go there, one interesting thing which happens when you apply this is you might ask the question, well, how does this, what kind of knowledge is this system actually learning? Is it learning to the same things that humans learn, or is it learning something radically different? And so one of the things you can ask about in the game of Go, amongst many possible forms of knowledge, is what kind of opening sequences are learned. These are the kind of corner patterns that are played in the game of Go. They're called joseki. And what we saw was that over the course of training, so this is 72 hours of training in this kind of timeline here, and we saw that at different times along training, it started to discover and play well-known human joseki more and more frequently. So it was really kind of discovering all of these human joseki and playing them with a reasonably high frequency. But then what's interesting is that later, it actually learns to discard them in favor of its own novel joseki that humans weren't aware of. So later on, this is an example where this kind of very well-known knight's move, pincer joseki, was discarded in favor of some new variant which isn't actually played by Go professionals. And so it was actually learning new knowledge, like kind of overturning, in the case of Go, thousands of years of human knowledge that had been built up, and learning to actually, by self-play and introspection, to figure out a better form of knowledge than that which was known about previously. OK, what about other domains? So one useful game to turn to is the game of chess. So although chess, from a complexity point of view, is easier than Go, it's interesting for other reasons. Most importantly, it's actually the most studied domain in the history of AI, arguably. Certainly studied by Babbage, Turing, Shannon, von Neumann. They were all interested in computer chess. Some of them even created their own chess programs, some of the first chess programs. One of them even ran just on paper, because it was before there were actually systems to be able to implement these ideas. And it became the Drosophila of AI for several decades. The Drosophila is like the fruit fly, the organism that has the most experiments done on it in genetics. So it became like the Drosophila of AI. Most research in AI at least referenced the idea of computer chess for many years. And maybe also interestingly, these very highly specialized systems were built up over the course of this time that were very, very successful in chess. And this led to one of the big kind of watershed moments in AI where a program called Deep Blue defeated Garry Kasparov maybe 2 decades or more ago. And progress has gone on beyond that point, so that the state-of-the-art programs now in chess are indisputably superhuman. They're far, far beyond the level of what Deep Blue was able to play. And now, when humans play against computers, they have to take handicaps. So the question is, can a human still salvage a draw against a computer if it's kind of given an extra 2 pawns or something compared to the computer? And we also looked at the game of shogi, Japanese chess, which is a more complex game than chess. It's a larger board, it's a larger action space, because every time you capture a piece, you get to place it back as one of your own moves. You can place your captured piece back as one of your own anywhere on the board. So that gives a huge branching factor and lots of rich tactical possibilities. And it was only relatively recently that world champion level programs were actually achieved at all with shogi. And through all of these domains, the state-of-the-art engines were all based on a particular approach that had been developed over decades, which was based on alpha-beta search, a kind of with handcrafted evaluation functions, typically optimized by human experts, human grandmasters, using these very careful search extensions with a lot of game-specific heuristics. So we compared to a particular program called Stockfish. And if we just kind of have a look at what's inside Stockfish, Stockfish is a really beautifully engineered example of a chess program. And it has inside it many, many pieces of knowledge. Some of these are really very general that could be applied to other games. But some of them are very specific to chess and use a lot of chess-specific knowledge of different types. And really, you can think of each one of these kind of ideas in here as something which represented, someone's PhD or several years of research, and then eventually kind of became a big success for computer chess that led to the next generation of chess programs being much stronger. And so these were built up over multiple decades to lead to Stockfish, which was the indisputed world champion. There are many, won multiple world championships. Maybe indisputed slightly strong, but very, very a multiple world champion winning program. And what we did was basically to get rid of all of them, strip them all out, and go back to the basic principles to say what happens if we just go back to the principles of deep reinforcement learning and start entirely with something that's based on reinforcement learning and deep neural networks, nothing else. Okay? Can we achieve the same level of performance? And the answer was that, surprisingly, when we actually trained this system by self-play alone, starting from scratch, that after just 4 hours of training, it was able to defeat Stockfish, this world championship program. And at the end of training, it was able to win by 100, well, in a 1,000-game match, you get a lot of draws at high-level chess, but it won 155 games to Stockfish's 6. I should say, by the way, that 4 hours of training, this is on Google infrastructure, so that might mean quite a lot more than 4 hours for many of you. We also tried in shogi. In that case, we played against the world champion program Elmo, and we were able to beat that program Elmo after just 2 hours of self-play training, and eventually able to win more than 90% of all the games against Elmo. So the strategy was successful, and in this case, it's an example where we're able to generalize, at least amongst this class of board game, to a much bigger space of possibilities by taking seriously the premise that, that if we actually formulate these things as RL problems and actually find general purpose solutions that work across many of them, that actually we can go much further if we're able to solve that and apply that to many different things than if we find dedicated special purpose solutions like the ones which have been used in the past. Okay. AlphaZero has been used elsewhere. I don't want to dwell so much on work that's happened inside my lab or anywhere else within DeepMind. I just wanted to actually give 2 examples of interesting work that's happened elsewhere. This is 2 Nature papers, one from a couple of years ago, one that just came out like 3 days ago. So, so I don't know the details, apart from having just very briefly had a look at it. But the first one is actually an example, it's called AlphaChem, and the idea was to apply the AlphaZero pipeline to chemical synthesis. So you have these kind of, it's called retrosynthesis, where you kind of have a goal of a particular chemical that you're trying to generate, and you try to figure out what pathway of chemical reactions you should go through to actually synthesize that particular chemical. And it turned out that AlphaZero was able to defeat the previous approaches in that kind of regime and do much, much better. This new paper is actually about quantum computing, where they showed that you can actually significantly outperform the state-of-the-art for estimating the dynamics of quantum computing systems, which is a really important problem in quantum computing, to really understand those quantum dynamics in these incredibly complex phenomena. And what they showed was that AlphaZero really did very well, outperformed the state-of-the-art. Go read the paper, because I don't know all the details. OK. So you should be wondering at this point, OK, we started at the beginning with this grand vision of trying to do reinforcement learning in any problem that you might be have thrown at you. And those problems, the reinforcement learning problem is designed to deal with unknown environments, Like you should be able to drop yourself, your robot or whatever it is, into some real-world environment where you've got no actual description of how the world works. And it should figure out for itself through experience, through interaction, through trial and error learning, how to succeed in that problem. So the example with Atari at the beginning using DQN was one such example. That was done in a way where it really learned through trial and error interaction with the environment to do better and better and better. The examples with AlphaGo and AlphaZero, on the other hand, we actually were supplying the rules of the game. We were telling it, one important piece of knowledge, which is how the world works. Like, how does this game of Go work? What are the rules of chess? What are the rules of Go? Now, if you take that to your robotics example, that would be equivalent to giving very detailed information about the kind of the dynamics of the world and the physics of the robot and the fluid dynamics of governing the air and all these other things. And we need to get past that eventually. So what we tried to do was to take an important step with this approach that we used in AlphaZero, which was to take away that piece of knowledge and get back to a full reinforcement learning system, which really is fully learning through trial and error in environments that are fully unknown. So to take away the rules, in other words. And so what we did was we recently introduced this. This is just out on Archive a couple of months ago. And we built a system called MuZero, where Mu basically stands for model. And the idea is to actually have the same kind of approach as AlphaZero, but planning now with a learned model. Okay, so it has to figure out the rules of the game, has to figure out the dynamics of the environment, and then plan with those rules or with those dynamics that it's learned, and all of the errors that may lead to, and deal with that. And the question is, can it still achieve high-level performance? Can we still get these impressive results and human-level performance? And can we still do it in a way that's completely general, such that it spans not only the kind of domains we were talking about before, chess, shogi, and Go, but also these much messier environments, which have typically been characterized by things like the Atari example, where people in the past hadn't been able to get much success using systems that learned a model and then planned with that model, because the world is just much messier. It's a much harder thing to model. It's much more. It's still a game, but it's got that characteristic of the real world that it's high-dimensional. There's lots of visual pixels coming in, and to understand how these pixels lead to these subsequent pixels is just a hard thing, and it's going to have errors in it if you try to model that. OK, so that's the thing we try to do, to kind of unify these problems and have a single system that can kind of do well across all of these. And so the particular approach that we took has the following motivation, okay, which is we should only predict the things that matter for planning. So if you build a model of the environment or build a model of the rules, actually, it doesn't matter if you characterize the real world. That's not the game we need to play. It doesn't matter if you get all the details of what's going on in the weather in Japan right now. I'm here in this room talking to you guys, and those details are essentially irrelevant to me. What matters is my subjective understanding of what will happen next, so that I can maximize my reward, whatever that might be, in talking to you guys, maybe keeping you all in the room so you don't run away. And if you can build a model that has all of the things which are necessary for optimal planning, then you're done. Like if you build a model that's such that when you plan with it, you really end up taking the optimal behavior, that model is good enough. Okay? And so it's trying to build the minimal thing that we really need to solve the problem, rather than building a model that captures all of the irrelevant details that maybe we don't need. That's the essential motivation here. So try to just predict the things that we need for planning. And in our case, for AlphaZero, what are those things? What are the things that AlphaZero uses for planning? Well, it uses policy. It has the policy network. It's trying to predict and suggest actions. It needs to estimate values. It's got a value network that's trying to say who's going to win from any position. And it has rewards. It needs to understand now, if we're going to go to more general domains, we need to understand whether we're going to get rewards along the way. Those are the things we need to plan effectively. OK, so how do we do this? So the basic idea then is to, first of all, look at what would happen if we were to plan with a learned model. What are the components that we would actually need? And then let's think about how to learn them. So if we were to plan with this learned model, we might start in this, say, Go state here. And we would first of all need to kind of build up some representation of where we are, like a state representation. Say, OK, well, this Go position corresponds to this embedding, this state, this kind of, think of these as the features describing what's going on, okay? And if we had that state describing what's going on, we could use that state to predict both our policy and our value. So from this state, what action should I take and who's going to win? Those are the things that we needed in AlphaGo, right? But we need one new piece now as well, which is we need the ability to kind of project ourselves forward in time. We need to say, well, I was in this state. What's going to happen? What's going to happen to the board next if I actually take a particular action? And so this is the dynamics now. So we've got this second function, this G function here now, or third function. We had this representation, prediction, and now we've got this dynamics model, which basically says what's going to happen to my state if I take a particular action. Okay? And if I have all of those things, then I can search, I can do planning. Okay? I can just roll this ahead. I can make a new prediction now about what will happen in this new state. I can imagine even more into the future, make new predictions, go further into the future, and so on. So the new piece really is we need to have this dynamics in addition to, we need to be able to build up this representation, make our predictions, but also kind of roll this representation forward, understand what's going to happen to my state if I take particular actions. What will the world look like if I take a step to the left or if I take a step to the right? Where will I be? That's the fundamental question that we need for a model. Okay. So the way that mu0 then actually learns this thing is it breaks this up into two phases, a bit like AlphaZero, a lot like AlphaZero. It first of all generates trajectories using search. So this is just like in AlphaZero now. It's basically, in each position, we're going to run a search, and we're going to take whatever our policy suggested, and we're actually going to play it, and that's going to be our move. We're going to run another search, take that thing, play it, run another search, take that thing, and play it. So again, this is our high-quality trajectories that we get from actually acting using our best ability to plan. Okay? But now what we're going to do is we're going to kind of line these two things up side by side. We're going to line up our imagined trajectory that we're going to use if we're planning ahead. So let's start from this state, and let's imagine what will happen if I was going to take this state A, if I was going to start in this state and take this action, and then take another action, and then so on. Where would I end up? Okay, this is my imagination at the top here. And from each of those imagined states, we're going to make predictions about what would happen. So this is exactly the quantities that we needed when we were searching. This is what happens in your head as you imagine into the future. And what we're going to do is line that up to reality and say, okay, well, in reality, I really took that action, and I really took this action, I really took this action. So I want to make sure that when I imagine with those same actions, that I get the same kind of predictions that I end up seeing in reality. So we're going to line these things up and make sure that our policy predicts what the search actually ended up doing at each of these steps, that this policy ends up predicting what our search really did, and that the value function ends up predicting the value which you actually ended up getting along that trajectory, like essentially the winner of the game, if you like. And also we need to line up the rewards and make sure that our rewards predict the rewards that you actually see. So we just need to make sure that we update this learn model so as to get the policy, the value, and the reward right. And everything else just happens kind of by backprop. That, what about this G thing? What's telling it the correct G? Well, nothing explicitly says what that model should be. It's just finding the G. It's finding this dynamics model. It's trying to find a model of the world which leads to all of these predictions being correct. So it's learning to imagine things into the future in such a way that it preserves all the quantities that we actually need to be able to plan correctly. Okay, that's mu0. Hope you got something from that. Right. And then we just go around this cycle. So we search using that model. We generate trajectories using the search. And we take the imagined trajectory and we line that up with reality, and we use that to update our model. And we just iterate that process, starting from scratch. So how does that do? Now, how does that really do now when we start completely from scratch, no rules? Can that compete with these kind of systems like AlphaZero that were given the perfect knowledge of the game and were able to use that to search effectively? So let's start with Atari. So in Atari, it turns out that this approach, mu0, not only defeated the... So before we were looking at systems which got a median performance of 75%. That was the DQN result, which I started the talk with. So this system gets a median performance across the 57 Atari games of 2,000%. and defeats all of the previous methods that anyone had used in RL, which was quite a number of ideas over the last 5 years. And that's using a lot of data. So that's when if you're able to run this for 20 billion frames. So then you might ask, well, OK, what happens if you use a more restricted amount of data, like the previous kind of work I was showing you? Is this just effective because it's using more data? Well, we tried a variant of the approach, which kind of goes back over old data, but is restricted to 200 million frames of data, which is kind of the standard in the research community. And we saw that, again, there's a huge jump in performance, getting still something like 730% median performance compared to these previous best. These are all the previous best approaches above that. So it works very well in these kind of messier domains like Atari, where deep RL has been successful in the past. But it also works very well in these very precise kind of planning domains like chess, shogi, and Go, where it has to learn the rules and then use those rules to play. And so what we see is that in each of these cases, this kind of orange line is the previous best version. And we see that over time, it actually learns to reach that level of performance. And in fact, it doesn't even take very much longer in terms of training. It's about the same speed as those previous versions. It turns out that for these games, the intuition is that learning how to play the game really well is harder than learning the rules. And so it's just implicitly learning the rules along with everything else, and that just kind of falls out along with the rest of the performance. OK, so we ended up getting state-of-the-art across those domains. One thing which we wanted to check is whether this is really scaling effectively. Like, does this scale? Now we've kind of learned a model. Does that model have errors in it which won't scale as you kind of look into the future? So we tried searching a lot longer. Like, we actually trained this thing using kind of searches which are about 0.1 second in thinking time. So we asked the question, well, what happens if we now actually run our program using, say, 50 seconds of search? How well does it actually do? And it turns out that even though it's kind of going far beyond the horizon for which it was trained, it still does very well, suggesting that it's actually learning a model which is kind of rolling out effectively far beyond the horizon that it was actually trained for. So that was encouraging. We also see that if you ask the question, how much does search help during training? So this is now a plot that shows each of these kind of blue lines of increasing darkness shows how much, like an increasing amount of search during training. Like, this is now how much search we actually do in the inner loop of our training process, where we're actually running search to pick our moves. So this is saying what's the quality of, how much are we kind of improving the quality of our actions by running our search. And the more search we do, the better performance gets. It actually really is helping the training algorithm itself to get better and better performance, even when you evaluate it with a fixed amount of search. And this one's just a baseline to show this is kind of a comparison on the same domain to kind of standard model-free approaches like the best Q-learning based baseline. OK, that was it for new work. I wanted to share that one thing. I've got one last piece. I don't know how we're doing for time. Everyone's still in the room large by, so I guess I'll carry on. I wanted to talk about StarCraft as the last example of deep reinforcement learning in a really challenging environment from the perspective of games. And I wanted to talk about our program AlphaStar, which became the first program to defeat a professional StarCraft player. So first of all, I guess we should ask, well, what is StarCraft? So I guess not everyone knows about it. It's a real-time strategy game, which means that it's a bit like a giant game of chess that gets played in real time, where you have to collect resources from this very large map and use those resources to build yourself a base. And that base enables you to build more and more sophisticated units. And those units allow you to go and defeat the opponent by kind of beating up their base, if you like. So that's the game. Why StarCraft amongst all possible things we could look at? Well, amongst video games, many people think of this as the kind of the one which is at the peak of human ability. Like, StarCraft represents amongst all esports that are widely played by humans. If you ask a lot of esports player, over the last 2 decades, this has been the game which consistently and with enduring length has been picked out as the best example of human skill combining like high-level strategies with low-level, motor control. The whole kind of stack of human abilities is brought to bear in this game. It's been played by millions and millions of people over 20 years. And actually, in the research community, this kind of plot at the bottom shows 12 years of competitions that have been run in StarCraft with hundreds of different submissions. But until recently, there hadn't been a lot of progress, and it was considered to be a very, very hard game to actually get anywhere in. And the reason is, why is this so hard for AI? Why is this interesting for those of you who only care about applications? And these are some of the kind of dimensions of complexity that it has. So it's complex in the sense of the typical dimensions that you might consider, which are only very crude measures, but it has a very large action space. So in fact, because it's like this giant game of chess where you actually get to, every single move you get to, if you like, simultaneously control hundreds of your own pieces at once. So every move itself has a huge amount of configurations that can be applied. In fact, there's about 10 to the 26 in our parameterization just for one move. That's the number of possibilities. And then there's about 15,000 such actions that you can pick before you get to the end of the game, and then you see like one bit of information as to whether you win or lose. So it's a hard case for really starting from, just trying to do this from reinforcement learning. It has highly impoverished information. So it's both partially observed in the sense that there's this thing called fog of war, which means that you only see opponent units that are close to your own ones. Everything else is obscured behind this kind of fog, and you don't see things. But it also has this kind of camera view. You only get to look through your personal camera at the map. You don't get to see the whole map at once. You only get to see, like saccading your eyes, you only get to see the thing you're looking at right now. And so you have to remember all of the stuff that you've looked at before and integrate that information together into your understanding of what's going on in the game. And furthermore, there's this, actually, it gives like what's called a sort of economy of information. You have to decide whether you're going to invest actions into moving your camera rather than clicking other things, which could take your time and effort, just to acquire new information and look somewhere else. And it has very hard game theoretical challenges. So it's designed as like this giant game of rock, paper, scissors with these cycles of one strategy beats another strategy beats another strategy. And those strategies have actually been discovered and evolved as the game has been edited by the makers. They kind of have been patching it with more and more corrections to add more and more like these cycles to keep them as perfect as possible. And so it's very hard to find, it's got this very hard exploration problem where to even find one effective strategy is very hard. But if you're already in a space where you've got a reasonable strategy, you're kind of in this huge local optimum where you think that strategy is great. And now to discover some completely different strategy is really hard because you have to kind of pull away from the thing that's working really well for you and try all these things which locally are going to look worse until you kind of eventually find this thing which only in aggregation, if you get all the little pieces of the strategy correct, will end up being better. So it's got this very hard exploration problem. So that's some of the challenges of StarCraft. And so the way we went about this was really trying to go back to these same principles, reinforcement learning and deep learning, and combining them together. We did need to, in this case, start off by seeding it with some human data. So unlike AlphaZero, this is not starting completely from scratch. I think that's an interesting direction for future work. There's a remaining challenge here, which is, can we get past these hard exploration problems without using human data? That's an open research question. But what we did do worked out very effectively. This video here, I think, is fun to see. This is what pro play looks like. So this is a top professional player actually playing the game of StarCraft. And it's just fun to see what this actually looks like. Have we got audio for this? There we go. So those clicks you can hear are this player actually playing something like over 300 actions per minute. And each of those actions, they're not just random actions. These are very strategic. He's kind of moving the camera around. He's figuring out how to build his units, how to expand his technology tree, how to coordinate all of those units together into configurations that work locally, to kind of wall off particular areas of his base with particular combinations of units, to move the camera around, to go scouting the enemy's base and understand what's happening in the enemy's base, all while trying to coordinate his own units at the same time. There's a lot going on. And so just fun to see that. Yeah, this is real time. I know why you asked that. No. OK. Sorry, where's my... Okay. So how did we do this? So I'm not going to go into all the technical details, but I'm just going to try and give you a sense of how this was done. So one of the challenges was actually to even deal with this incredibly complex action space that you have in StarCraft. And the way that was done was using this kind of auto-aggressive actions, like this policy which step by step figured out a piece of the action and then said, OK, if I've chosen that piece of the action, now what should the next piece of the action be? Now, if I've chosen that piece, what should the next piece be? And so, in particular, we kind of divide this up into what, when, who, and where. So these auto-aggressive actions, first of all, have to pick, what type of action are we going to do? Are we going to move our unit? Are we going to send our unit to attack someone? Are we going to build something? What kind of unit are we going to build? All those kind of things. When are we going to apply that action? So actually, one of the ways we dealt with this very long temporal sequence is to allow the actions to pick their own delay. So they commit to how many steps should it be until the next action is chosen in the future. So it's like not only deciding what to do, but how long do you then wait until you pick the next thing. Who should this be applied to? So this is basically actually something which goes around all of our units, kind of pointing at them, saying this one, and this one, and this one, and this one, and this one. Each of those is its own autoregressive step, saying, I've already pointed at this unit, and this unit, and this unit, and then it gets to kind of point to the next one. There's a particular deep learning architecture that lets you do that differentiably. And finally, where should it target? So for many actions, for example, to move or to attack, you need to specify a coordinate or another unit that you want to send your actions towards. So this is all combined together into a deep neural network, quite a sophisticated architecture. And that neural network architecture was initially trained by supervised learning, which allowed this system to explore human-like behaviors. But then the thing which we did in AlphaStar, which is kind of, I think, interesting and different from what was done in something like AlphaGo or AlphaZero, is we developed this thing that we called the AlphaStar League. And the reason for the AlphaStar League, the motivation for it, is to actually make sure that we cover all of the different corners of strategy space with this rock, paper, scissors kind of cycles in them. How do you even get to figure out all of those different strategies which are out there? And how do you make sure that you're not missing something? How do we make sure that we're not missing some potential counter strategy that a human might have that might be able to exploit our agents very, very easily? And so the way that we did that was twofold, uses two main ideas. The first of them is this idea called prioritize fictitious play, which basically means that you kind of keep all of your old strategies around and you carry on playing against those old strategies. And that means that you never forget how to defeat an old strategy. And in fact, the amount we play against those is in proportion to how well it's doing against us. So the better an old strategy is doing against us, the more we play against it, so that we kind of remember how to deal with that strategy again. And if there's a strategy which we can't figure out how to beat, we play it and we play it and we play it until we do figure out how to beat it. And so the inner loop of all this is reinforcement learning. But I won't go into details of how that RL works. It's kind of an actor-critic architecture for those of you who care. The second main idea is to have these things called exploiters. So that's the idea of this league over here. You see, we start off with these supervised agents. And then for each of these three races represented by the circle, square, and triangle, there's one agent for each of the three races. We have one main agent that's being trained, and each of these things represents kind of one of these old strategies that we're keeping around, and we keep getting better and better and better. But we also train these dedicated exploiter agents for each race. And these exploiters, their purpose is not to be strong. Their purpose is to find weaknesses of the main agent. So they're basically specializing, trying to find ways to beat the main agents without worrying about whether they're themselves strong. And so the main exploiters are trying to beat the main agents, and the league exploiters are trying to beat everyone without having to be exposed to exploitation in turn. And the whole point of having these things is that now the main agents end up playing against these exploiters, and so they kind of now have opponents that are potentially actually trying these interesting corners of strategy space, and it has to figure out how to deal with those different counter strategies and develop its own counter-counter strategies. So it's a way to kind of just get coverage of all the corners of this very complex kind of cyclic space of strategy dependencies. So that's the AlphaStar League. When we train this system over time, what we see is again, this is a kind of ELO scale here, is we see the main agents getting stronger and stronger and stronger, but indeed you see that some of these exploiters, they don't get stronger at all. They're just learning these kind of potentially pretty rubbish strategies, but those rubbish strategies are very effective against some of our current agents, even though they're not kind of generally strong themselves. And so they're really useful to have in there, because now these guys have to kind of learn how to deal with all of these strange strategies, which actually represent things that humans really do. If you watch games that humans play, they're always trying these things called cheeses, which are basically the corners of the strategy space, like Cannon Rush, or these weird strategies that no one would even think to try unless you've played these games for years. Okay, so that's the training progress. And then briefly, just how does this thing actually do in practice? So this is a fun video. This was actually Oriel and myself. Oriel was the co-lead of the project. This was our first ever victory we had against a pro player. And embarrassingly, you can see our reaction to what happened when we saw this game happen. So this is a player called Liquid TLO, and he's one of the top players. However, in this particular match, he wasn't playing his strongest race, but nevertheless, it was the first time that anyone had been able to actually defeat a pro. Okay. And we actually ended up winning that match 5-0 and played against a subsequent player, Liquid Mana, who was even stronger. That one was 5-0, but with a final game that we lost of a different type. Anyway, what I wanted to talk about was what came afterwards. So recently, just a few months ago, we published a paper showing that we'd pushed this a bit further. And so what we tried to do was, that initial demonstration was just for one of the 3 StarCraft races. Now, we tried to move beyond that to play the full game as humans play it when they play online and under tournament conditions, play in the way that humans play, no caveats, exactly the full game, exactly all the conditions, exactly the way they do it, as much as possible. Exactly is always hard. Okay, so first of all, we played all the races and more maps. Just as you can, and we evaluated it on the same online server that humans play on. We gave players this opt-in where they were able to choose whether they wanted to play against AlphaStar, and amongst the players that they opted in, which was more than half of all players on Battle.net, we then played a couple of hundred games with different configurations of AlphaStar for all 3 races, and these are the summary of the results. But you see these percentages here are essentially, this is the percentile of human skill level that we achieved for each of the races, so 99.9%, 99.8%, 99.76%, amongst human skill levels that amongst the hundreds of thousands of human players on Battle.net. So the other thing which we tried to do was to make sure that we were playing in as human-like a way as possible. So you saw this human who was clicking extremely fast, 300 times per minute. And what we wanted to make sure we were doing is not winning just because we were clicking faster than the human. And in fact, that first demonstration match that I showed you, there was some legitimate criticism of the way that our agent had actually been counting its speed, its clicking speed. And so we were very careful in this evaluation, and pro players were happy with it. It was done in a way that the pro players agreed was reasonable and corresponded to human speeds and rates of clicking and latencies. So they were happy with that. And most importantly, we moved to something which really was, as I mentioned at the beginning, using this full kind of saccading of the eyes, this kind of idea that you only get to look at a part of the view at a time, whereas that initial demonstration match was actually able to see the full map all at once. And so this is really playing in the way that humans have to. They really have to move their camera view over to here if you want to find out what's going on, see what the opponent's doing, remember that, click back over here, decide exactly when you want to accumulate information by clicking somewhere else. Okay. So this is a visualization of the percentile of human performance. And you see the different leagues that humans play in. So they're divided up into bronze and silver and gold and platinum and diamond. And then you get to the Master League. And then beyond that, you get the Grandmaster League, which is basically where AlphaStar is sitting. So it achieved Grandmaster level performance for all of the different races in StarCraft. And that's actually the first time that the top league of performance has been achieved using the full version of any full esport game. A lot of other games people have looked at, but there's always been certain caveats or restrictions and simplifications of the game itself. Okay. I just wanted to finish by pointing to work and say, not everything we do is games. There are real applications. This is work that was just published in Nature a couple of weeks ago. And this is something called AlphaFold. It was a system that was trained using deep learning and some ideas that were drawn from search. More like a different kind of search, more like to try and optimize over the landscape of different ways to fold a protein. And this is a huge problem in biology that has enormous real-world application, which is to ask the question, amongst all possible ways that you can, if you consider a particular protein sequence, the sequence of amino acids, if you're given that sequence, and you want to know what does this thing do, the most important way to know what it does is to know what shape it will actually make when it's actually placed inside the body in nature. And that's the protein folding problem, is to predict what shape, what's the form of protein that particular sequence will result in. And so at DeepMind, I was only a co-author on this, but most of the work was done by other people. There's a system called AlphaFold, and the idea was to try and build a system which basically just predicts this directly from the raw input and estimate what that actual shape of that thing would be. And when it was analyzed in the biannual assessment, this is a very formal assessment that happens for protein folding systems. And you can see it was actually far beyond any of the other systems that were evaluated. So it's the current state of the art by quite a way for this very important biological problem. Although there's some way to go for this actually to be good enough to, for example, design real drugs. So there's still some work to do to get to the point where these things are realistic enough to do that. So I just wanted to finish by an example where it's not all games, but I think games can take us a long way. We learn a lot from them. And the main conclusion of this, if you like, is to really say, we should at least consider the power that is offered by these systems that combine the problem of reinforcement learning with the power of deep learning, and ask ourselves, how far can they go? And I guess this talk has been some illustrations where maybe they can take you further than you might have predicted in advance of seeing these, but there's still a long way to go. Some additional resources here. Happy to take some questions. I've probably gone way over, sorry. Thank you. Is it OK to take a few questions, just organisers? Or if anyone needs to run away, then just run away. And then, yeah, I'll take maybe 5 minutes of questions. Yeah.
How about where the game itself is always changing, which is more like what life is like, where nothing's ever quite the same?
I can also just repeat the question.
Yeah, what about when the game itself is always changing as it does in life? How much have you done with that?
Yeah. So that's a great question. Let me give a few different answers. So answer one, which you should probably find unsatisfying, but is that any non-stationary system is equivalent to a really big stationary system. So in some sense, if you can deal with really big systems, you can already deal with non-stationarity. That's answer one, that maybe you don't need to do something special. Or if we flip it around, I prefer the flipped view, which is to say, so let me give you the flipped view, which is to say, even if your problem is stationary, if it's big enough, if the world that you're trying to interact with is big enough, such that it's much, much bigger than anything your agent can deal with, like in Go, we've got 10 to the 170 states. There's no agent that can deal with all of those states. So it's actually useful for the agent to treat it as non-stationary, like to only deal with the part of the world it's actually having to face right now. Like I mentioned, I don't need to model what's going on in the weather in Japan right now, even though that might be relevant to me. But if I later go there, that will be really relevant to me, and I'll need to model that stuff. So in some sense, I can treat the world as non-stationary even if it's not. And the third answer is really to say that I think that these approaches of RL, reinforcement learning, and deep learning, that many of the methods that people use are actually maybe unusual in the regard that they actually allow for non-stationarity to some extent in the nature they're trained. They are incremental learning systems that if stuff changes incrementally, that's okay. And in fact, it's almost the norm in reinforcement learning. So in reinforcement learning, whenever you do reinforcement learning, you face the situation that you learn a policy, and then later on you behave according to, you learn a better policy, and now you behave according to that better policy. It takes you somewhere different, and the data you see is different, and now you have to learn, and the value of that policy is different to what your value was before. So as your behavior changes, the thing you're trying to predict, like your value function, like how well you'll do, actually changes anyway. So it's inherent to the RL problem, non-stationarity, that you're continually having to update your estimate of your value function because your policy just gets better and better and better, and that's a source of non-stationarity. So we just have to deal with it. And I think a question is, are we doing enough? Well, probably not, and there's probably better things to do, but you at least have to address it already to get to these kind of level of results. There's some element of non-stationarity already being dealt with. Okay, next question. Yeah.
Hi. Yeah, thanks. Great talk, David. No, so I would, kind of like to dig a little deeper into your definition of AGI.
Yeah,
it seems like all of these methods, although they're giving great results, are statistical, right? So I would define general intelligence as something that has subjective experience and self-aware. So how is statistical methods going to get us there?
Okay. So let me. So self-awareness in your first one was? Subjective. Okay. So subjective experience, again, let me give a similar answer to the first point, which is all of these methods are inherently about subjective experience. Okay, inherently. These approaches to RL, the agent is inherently subjective. It's trying to learn about something. It's trying to build its own knowledge representation, its own value function. That's it's not trying to learn any objective knowledge about the world. It's trying to learn, for this sequence of experience that I have received as an agent, what does this lead me to believe about the world? And if that happens to be different to someone else's experience and how they think about the world, that's fine, and it can still lead to good behavior. So I think subjectivity is inherent to the way that the RL problem is formulated. We're explicitly not trying to think of the world as something which is known or given, but it's just something which is out there and which the agent only sees through its interactions. Self-awareness, it depends what you mean about it for self-awareness. I mean, this is bordering on questions of consciousness, which have many different definitions. Let me say it this way, that if there's a utility to your definition of self-awareness, in the sense that if by being self-aware, an agent is actually able to get more reward in its environment, then inasmuch as that is your definition, the RL problem deals with it. Okay? For any aspect of consciousness or self-awareness that sits outside that, then RL has nothing to say about it. But on the other hand, you should also ask the question, if it's not giving you utility and getting more reward in the environment, should we care about it? Is this a useful aspect of intelligence to think about?
You might ask, would we have evolved any such aspects of intelligence as well?
Right. So evolution is if something has evolved, perhaps there's an argument from an evolutionary perspective that has utility. Yep. Okay. I think this was the first hand up.
So in most of the games, it's quite clear what good looks like as you win the game at the end.
Yeah.
But in the world, we are working out what good looks like as well as playing the game. So we don't know necessarily what, what the good outcomes.
Yeah. So the question is.
How would you learn those sorts of good values?
So to paraphrase those who didn't hear, the question was essentially, what happens if you're not given the reward, but you kind of have to figure it out. So I think of the reward as part of the problem definition. So if you don't know what your agent what you're asking your agent to do, you shouldn't expect it to do it. So at some level, there has to be a clear definition of the problem. There has to be a clear objective. And it has to be formulated in some way. Now, it might be that what you're saying is that sometimes the only way I know good behavior is when I see it. That it's like that the only way that I could possibly recognize whether the robot is doing something I want is by me observing it and saying, yeah, that's good. And that's a perfectly legitimate reward function, but it's one that happens to have a human in the loop. It's one where me as the human labeler is now part of the environment, labeling what's happening and saying, OK, well, that's an environment in which the robot did this thing, and then the human that was labeling it said that was good and gave it a +1 reward, or the human gave it a -1 reward. And that whole thing now comprises the environment, and the role of the RL agent is to do well in that environment. I know a lot of people seem to worry about this problem of where rewards come from, but I think fundamentally we need to come up with systems that are able to deal flexibly with any goal that we ask them to achieve. And we have to be able to say what that goal is. Otherwise, what are we doing as problem designers?
Yeah, but there's often side effects, and like if you ask it to do something and then it finds some crazy way of optimizing.
Yeah, there might be side effects. That just means that you thought you knew what the problem was that you as the problem designer, but you didn't. I mean, that's inherent to the problem design, but as we go more and more towards the real world, I mean, let me just say again that there will be side effects. I think we need to be clear about what the problem is and accept that our role is, maybe let me say it this way. I, as a researcher, will be happy if I can arrive at a system which, given any goal, can learn to achieve that goal. And I'm agnostic as to where that goal comes from. I just want people to give me completely clear goals. OK. All right. Question in the white shirt.
Hi, I just had a question about the board games. Do you consider them solved? Or do you think things like the cycles you've seen in the AlphaStar could be relevant to the game of Go, and we didn't see some of these patterns? Or things like the fact that you train against fixed other agents, like for the shogi and chess, and can't win against them 100% of the time? Does this mean that you can still do better?
OK, so let me take two definitions of solved. OK, so if you mean by solved, far better than humans, I think we're there for those games. OK, I don't think it's the case that if you allowed humans to just play and play and play, that they would magically become better. I think that we're at the point where those programs are superhuman now. I think, on the other hand, if you ask how much room is there to get better, certainly in Go, there's limitless room. Like, I mean, for any level of performance we achieve, this is a game that there's no draws. So there will always be, there's 10 to the 170 states. So unless you can perfectly represent all 10 to the 170 states, there will be a strategy that beats your one that exists somewhere in that space, and it can exploit your inaccuracies in your approximation to it. So for many, many future generations, there will always be a program that can beat the previous one 100% of the time, effectively, 99.9%. For chess, the situation is slightly different, where chess is presumed, no one really knows, but it's presumed to be a first player draw. So it's under optimal play, it's a draw, people think. So that means that as the players get stronger and stronger and stronger, they get closer and closer to 100% drawn outcomes. So we may already be close to the point where no future program could win games against the existing programs. It seems to be getting harder and harder to beat previous programs. So I think it depends on the game a little bit. Yeah, the lady towards the back. Yeah.
So the question is a very basic one, more about the training of AlphaZero.
Yeah.
So when we get rid of the human data and now we want to find these moves on our own, the policy value break the network, is it just random values? How do you, when you start, like what is the
What's the starting point? The starting point is a randomly initialized neural network. So the weights are drawn from the usual weight distributions that you have for initializing a neural net. And so the output of that neural network is whatever it is. So it'll be for certain positions, it will be predicting a win, and certain other positions it will be predicting a draw. It's actually a continuous scale between +1 and -1. So it's going to be somewhere in between. And for the policy, it's very close to uniform random, but there will be some biases in that because it's not a perfect randomizer amongst actions.
Training time more complex when you have a game with a higher number of permutations. And in that case, how would you know that it's just bad initialization versus good initialization? How do you know when to stop training?
Okay, I think there were two parts to that. I think one was about initialization and one was about stopping. So I think for initialization, I don't think we've seen evidence that the initialization is tied to the complexity of the game. In fact, maybe the opposite, that neural networks are very effective at dealing with high-dimensional spaces. So they can learn high-dimensional functions. And really, the difficulty of doing so depends on the complexity of the function you're trying to learn, not like how many states there are in the actual problem or anything like that. I think for the stopping time, I don't really have a good answer except that we stop when we run out of compute budget, which is probably beyond when most other people could stop.
I had a question.
Yeah.
Can you talk to us about the data efficiency of the learning systems that you've spoken about today and compare that to the data efficiency of human learning?
Okay. So the question was about data efficiency compared to human data efficiency. So let me start with the board games and say that in that case, we tend to learn from around, say, 1 million actual games of self-play that so order of 1 million, which is clearly beyond what any individual experiences in their lifetime. However, you might also argue that a human starts by taking on board the knowledge of previous generations of players. They read Go books that have been formed by other players that are based on thousands of years worth of games. And if you look at the history of Go, that's more than probably around that order of magnitude of games in that kind of pyramid. For StarCraft, it corresponds to something like, I think it's, each agent in the league, I believe, sees something like, I think it's maybe around 100 years worth of experience. So it is quite a lot and more than a human would see, but it's not many, many, many orders of magnitude further. I could be wrong about that number, so I apologize. And for Atari, as I mentioned, we explored more or less data-efficient methods where you can actually go back and reuse data to try and be more sample efficient. And so that if you do that, it corresponds to a small number of hours of gameplay. Really depends on the level of performance you want to achieve. And if you really are focused on sample efficiency, I'm sure you can do better. We weren't focused on sample efficiency for most of those examples.
I guess with StarCraft, the players are not really relying on generations of StarCraft players before.
Not generations before, but they do learn from other players quite a bit. Okay, I'm going to take one more question, I think. How about right against the wall over there?
Yeah, so I had a couple questions about sort of your blooper reel. When you create an architecture, how often you have to change that before you actually get effective results?
Yeah.
And do you see going forward that the agent could actually parameterize the architecture?
Okay. Those are both really good questions. Parameterizing the architecture is an area of recent research, like neural architecture search, that I think it's. I don't personally feel like we have the right approaches yet. I feel like they're very brute force and essentially amount to trying everything for all these different architectures at great computational expense. I think in principle, yes, but I don't think we have the right methods to do that yet. Okay, so that was the second question. In terms of the blooper reel, let me give you two So one of the nice examples was actually shogi. So it depends on the domain a little bit. So shogi was one of the good cases where actually we went about trying to build AlphaZero, and we mostly tried it on Go, and then we were trying to see what would happen in chess. We mostly focused on chess. And then there were a bunch of bugs that we had to go through. And so to answer your question, it's like anything, whenever you're dealing with anything, there are a whole load of bugs resulting from just making sure that the rules were connected correctly, that we're dealing with repetitions, right, and all the little details of chess, and that the architecture was able to express those in a reasonable way. Once that was working, we then tried it on shogi, and the results that we showed in the paper are basically the first time we ever ran it on shogi. So we didn't really need any further iterations once we'd got it right for chess to apply it to a game which was sort of in the same family. So the reality, I think, is somewhere in between, that you need to get the architecture right. We don't yet have a magic solution. I would love to have the magic box that figures out the architecture automatically. At the moment, we don't have that, and it does require it makes a big impact on performance. So for StarCraft in particular, there were many iterations of getting the architecture right, and that was done largely by supervised learning to just forget about RL, just sandbox the architecture problem, make sure your architecture works really well, and that you can actually learn the stuff you need to learn at all before you even think about RL. That's like just a basic principle of getting these things to work well. And so that was done in all of these domains, really. We did the same in Go, and we did the same in chess. But beyond that, I think it's a really interesting question to ask how you might simplify this. I would say StarCraft was at one extreme end where we put a lot of effort into the architecture. AlphaGo actually was a fairly standard convolutional neural network architecture. We did iterate it, and improving the architecture did lead to big performance wins. But even with a vanilla architecture that you were using for say, something like ImageNet, actually gives very strong performance in Go. So it's not like you have to do all that stuff, but it does matter, and it does lead to better performance. So yeah, reality is somewhere in between, I guess. Okay, thanks everyone. Really appreciate it.